In UniFi Network Controller, when you create a new firewall rule, if you go to menu, you can find 4 so-called firewall rule states listed here. You may wonder what they are. I mean, what they really are. In fact, just by reading the English words, you may be able to create working firewall rules in most cases. But if you are interested in what they really are from technical perspective, we have to talk about netfilter, more specifically connection tracking in netfilter. Netfilter is a framework provided by Linux kernel. It implemented packet filtering. UniFi routers are based on Debian Linux. It's also running netfilter to implement the firewall rule functionalities. And the netfilter include multiple components. You may hear of IP tables in the past. Connection tracking is also part of it. All the components work together to support netfilter, or in the context of UniFi routers, they work together to support firewall rule functionalities. And in this video, let's focus on the connection tracking. In the right side, you can see the IP table tutorial. It explains the 4 familiar states you already saw in the UniFi Network Controller. They are the 4 so-called userland states for Linux connection tracking. Just by reading the explanations, it is still hard to relate to real-world network traffic. Let's use several common network protocols. Let's see the connection tracking work in action and how they will impact the UniFi firewall rules. There are a lot of different opinions about how to set up firewall rules. This video is not about the best practice, so we will not talk about whether a given rule is good or bad. I will only show you in what situations you will see the 4 different states and how your firewall rules will be impacted by the state transitions. Okay? Just to understand how the firewall rules will be generated in the backend, let me create a random firewall rule. Create an entry, block VLAN 10 to VLAN 20, and let me say drop source type network VLAN 10 and destination network VLAN 20. Then enable menu. Let me randomly choose, let's say, new and invalid. Okay, add rule. Then let's go to the backend. So in the lower left SSH session, let me log on to the router. In my lab environment, I'm using UX3 Pro. So let me first show you the IP tables. And you can see this drop rule. This one corresponds to the one we just created in UniFi Network Controller. It's drop action and it will match the set. The source is VLAN 10. This is a so-called IP set. It's out of scope, but just by reading the name, you can already guess is for VLAN 10 network. The other match set is for VLAN 20 and it is destination. And this part is what we are going to talk about in this video, the CT state, connection tracking state. And you can see it will only match invalid and new states. We will only check IP tables in this part, and going forward we will only focus on the connection tracking. Now you can see in UniFi Network Controller, you select the match states and how they are represented in the generated IP rules is here in the CT state part. And in UniFi router, there is a user space tool. It's called conntrack. You can use this tool to show you the current connection tracking situation. Now it's time to discuss the 4 internal connection tracking states. So let's start with TCP protocol. On the screen, you see 2 Linux virtual machines. The left one in VLAN 10, the right one in VLAN 20. In the upper right, you can still see the SSH session to the UniFi router. And in the 2 Linux machines, I already launched Wireshark, and let me start capturing. As you can see, I already set the filter for both Wireshark sessions so that I only see the network packets I'm interested in. Let me start capturing. Okay, and then in the SSH session, let me run this command, connection track. The E parameter means I want to see the live events, but I only want to see the events which are related to the first VLAN 10 Linux machine, no matter whether it's source or destination. So let me run it. Started. In the VLAN 20 Linux machine, I have a website from VLAN 10 machine as a client. Let me run curl command against the IP address for the VLAN 20 machine. I'm also going to run the stopwatch. Later, I will explain why. Let me run the curl command. Then start the stopwatch right away. So see, in all the 3 monitoring sessions, you see some things happened already, right? In the SSH part, you can see the last event was update. Give it some time. In about 2 minutes, a new event will be generated. Let me keep the stopwatch running. Okay, we are close to 2 minutes. Okay. See that a new destroy event was generated, right? So stop it, close the stopwatch. We are good about the timer. So then let me stop the monitoring in all the 3 sessions. Let's examine what happened. For TCP traffic, the very first step is the so-called 3-way handshake. So the client needs to send a SYN packet, and then the router will treat it as a new one. Once the server receives it, server will send back a packet, SYN acknowledge. When the router sees the server's packet, it will change connection state to established. Once the client receives the SYN ACK, the client will send back a packet. It is ACK. So in this way, the TCP connection can be established. So once the connection is already in established state, the client and the server can do the communications, but the connection state will remain in established. And then once the client finish the activity, for example, in our case, the curl already got all the content back, the client will send a FIN ACK to close the connection. So once the server receives it, it will send back a FIN ACK, and the client will send a ACK. So once the router see the last ACK, it will set the connection state to closed. But if you check the connection tracking in the router, you can see once the last acknowledge is received by the router, the internal state will be changed to time wait. So internally, the router will not really completely close the connection. The reason is it is TCP protocol. It can tolerate some packet in the whole process received late, which means when the server receives the packets, the sequence may not be exactly the same as when the client sent them. The reason router will keep the connection in the time wait mode is just in case some packet may arrive late, so the router will still have the chance to send the packet to the target. But as we saw in the timer, after 2 minutes, the connection will be destroyed. That means it's done from the router perspective. You may wonder whether we can configure the timer. Yes, we can. See in the UniFi network controller under the firewall rule, there's a general setting, state timeouts. If you disable the author, you can see a whole bunch of timers, including the one we just saw. The TCP time wait is 120 seconds. If you want, you may try to mess up with the numbers, but for this video, I will keep all of them default. Then let's check the captured Wireshark packets. Start with the client. The client send a SYN packet to establish the connection, and then the server send back SYN ACK exactly as shown in the diagram, and then the client send back ACK. So after the first 3 packets, the 3-way handshake is done. You see the fourth packet is HTTP. HTTP is based on TCP. Between the 3-way handshake and the close connection packets. In the middle, the client need to retrieve the content of the web page. In the end, you can see the client send the FIN ACK and the server reply back with FIN ACK, and then the client send back ACK. I will not go through the details from the server side because it's similar to what we see from the client side. It's just from the server perspective. I believe after this simple demo, you see how a normal TCP connection works in action and how in the router side, the connection tracking is making the state change. We already see the new and established state. Let's do something to manipulate the router's firewall activities regarding the new or established state. Let's see how our firewall rule will impact this example TCP activity. Let me create a new firewall rule in UniFi network controller. Block 10 to 20. Action is block. Source type network VLAN 10. Destination network VLAN 20. For menu settings, let me only select new. Then start the capturing as we did previously. Then in the UniFi router, run the same connection track command. Now from VLAN 10, let me run the exact same curl command. See the difference? From the client perspective, the curl command just hang there. And in the Wireshark, you can see the first one is in blue color. All other packets are in black, which means they are retransmission. Why they are retransmitted? Because after the first packet, which is SYN is sent, it never received a reply from the server. That's why it keeps resending. And then from the server side Wireshark, you can see nothing has been captured. It doesn't receive anything. Then from the router connection track, nothing is tracked. So there's no new packet, there's no new state. Why is that? Because the IP tables or firewall rules blocked this packet. Why it's blocked? Because the state is new. I believe it's a very straightforward example. That's the effect if you create a block new firewall rule. What's the behavior from the client tool perspective, from the network traffic perspective, and from the connection tracking perspective inside the router? Let's test another simple example. Edit this firewall rule, block 20 to 10, and it still drop a source. Let me choose 20. Destination, choose VLAN 10. For state, this time establish. Apply changes. So before we test it, let's check the diagram because we want to block the established. This packet SYN should be able to send out and the server should be able to receive it. The server even can send out the SYN ACK, but SYN ACK will never reach the client, which means even the very first step for TCP to establish the three-way handshake, it cannot be done. It's just theoretical analysis by checking the diagram, but let's test it out. Start capturing and run the same connection tracking in router. Then from client, run the same tool. Okay, see the behavior is much different. From the client side, the end user's experience is the same. It's still hang there, but internally different thing happened. So from the client perspective, yes, it sent out the SYN, it keep resending because it never received the SYN ACK, right? From the server perspective, it did receive the SYN sent out by the client. It did send out the required SYN ACK, but because the router blocked it, it will keep resending. Then from the router perspective, let's see the first one, SYN sent. So it came to the new state. And then SYN receive, that's because the server did receive it. But when the server sent out the SYN ACK, it's dropped. So from the connection tracking, why you see so many SYN RECV? Because the client keeps sending the SYN, but server's reply never came through. So the situation is just all the three parties, they are just keep doing, and then in the end, you can see in the connection tracking, the state machine was destroyed. Remember we mentioned the timer setting. So then let's see for SYN receive, what's the timer? Go to the the UniFi network controller for timeouts. TCP sync receive 60 seconds. After 60 seconds, the state machine was destroyed. So we are good with the TCP examples. Let's move on to UDP. UDP is much simpler than TCP. UDP connections themselves, they are not really stateful connections, but connection tracking in router will still maintain state machines for the UDP connections. Before we start our testing, let me disable this test rule we created for TCP scenario. As you can see, I have two Linux machines. In the right side one, I have a Pi-hole server and it is in VLAN 20. We can confirm that by checking the IP address. Yeah, it's in 20 subnet. And from the same VLAN 10 client, let me run a dig command. The reason I choose the dig tool is to test the DNS protocol. You know DNS is based on UDP. Before running the command, let me start the capturing in both client. Change the filtering in the client side to DNS. In the same way inside the router, I will run the connection tracking, run the dig command. Now there's no firewall rule yet. From the dig tool, we successfully received the reply from the Pi-hole server and we got the IP addresses back. From the client perspective, it's a typical DNS query. The client sent out the query to the Pi-hole server and the Pi-hole server replied. From Pi-hole perspective, the client queried the domain name and the Pi-hole server replied. Then from the connection tracking, you can see the protocol is UDP. The first one will initiate the new state, and the second one, the server replied, it will update the state to established. And then because for DNS, the timeout time will be short, so very shortly you see the destroy event, so the state machine was done. So this is a super simple successful DNS query. Then let me enable the firewall rule. We still want to block 20 to 10 and we still want to block the established state. Resume. I will keep the 3 tracking sessions running, run the same command. See the difference? Let's check them one by one. From the client, it still sends out the same query as before. From the diagram, you can see because it's new, it won't be blocked and the server will be able to receive it. And let's confirm in the server side Wireshark. Yes, the server received the client's query, right? You can see from the server perspective, it sent out the DNS result. There's no any retransmission because unlike TCP, UDP doesn't do that. So the server send out the DNS reply back from server side. It's done. It's successful already. But because we blocked the established state, the client never received the reply from the server. So you can see what happened. The client keep sending the DNS query. But the reason the client keeps sending it is not because of retransmission happened. No, it's simply because the dig tool didn't receive reply, so the dig tool resend out the query. It did it 3 times. You can see the 3 timeouts in the dig results. It simply gave up. So the tool ended. That's why you don't see any new query from the client. And then from server perspective, the server was innocent. It didn't know the reply was blocked. So every time when it received the client's requery, it will keep sending out the correct reply. But every time it's simply dropped. They never reached the client, right? So it's very clear from both the DNS client and the server perspective. Then let's see what happened in the router side in the tracking. This is the first new one because the established state was dropped. The client keeps sending new one, and each new query will be treated as the start of a new state machine. So that's why you see the 3 new here. And the 4th new one, if you check carefully, the destination IP address is different. So this one is not relevant to our testing. In fact, it's network time protocol and it's also based on UDP, but it's not triggered by our testing. So then the same thing, the update one is also not relevant. Then you see the 3 destroy. Why destroy? It's simply because the state machine timeout. The per 3 new state machines only had new state and then they were all destroyed. That's what happened inside the router. And you can see for UDP, the situation is much simpler than TCP. Okay, move on. Now let's talk about ICMP. Whenever seeing ICMP, most people will think about the ping. In fact, ICMP packet may also appear in other scenarios. But let's start with the simplest ping scenario. You can see from the VLAN 10 client, I'm going to run ping to send out the ICMP echo request. Then it will create a new state machine, start with state new. When the VLAN 20 machine receive it, it will reply with a ICMP echo reply. State will be changed to established mode. Let me start the capturing and tracking in all the 3 sessions. Then from the VLAN 10 machine, run the ping command, and I will only ping 3 times. Run it. Okay, stop capturing. From client machine, the VLAN 10 machine send out echo request and the VLAN 20 machine replied with the echo reply. And the same pair of packets happened 3 times. In the server side, similar situation. Then let me enable the previously created block 20 to 10 firewall rule. And if you remember, we are blocking the established state. Restart the capturing. Then run the exact same ping command again. See, this time different thing happened, right? From the VLAN 10 machine perspective, it simply sent out 3 ICMP echo requests. It never received any reply because the echo reply was blocked by the firewall. From the server side, it's interesting. It received the echo request from client. It did send out a reply. And there was no error at all from the server perspective. And then the same thing happened totally 3 times. The reason is the VLAN 20 machine did receive the echo request and it did send out a reply. From the VLAN 20 machine perspective, nothing was wrong. There's no resend, there's no error. From the connection tracking inside the router, you can see it also created the state machine, and the update is simply because VLAN 10 machine sent the echo request again. It's not because the VLAN 10 machine received the reply. And then after its timeout, the state machine was destroyed. So you see the 3 echo requests from the client side, not because the client did the resend. No, it's simply because in our command line, we indicate count 3. The ping tool did it 3 times. Nothing was retransmitted and all the echo requests were blocked inside the router. Okay, so move on to next ICMP scenario. In this scenario, we will see the related state. So far, we have been seeing new established a lot of times, but where is related? You will see it here. So this is a special situation for TCP. You can see in the UniFi network controller, there's no firewall rule enabled yet. From VLAN 10, I already started the firewall rule. As you can see, I filtered the display setting to TCP or ICMP. You will see why I use ICMP here as well. In the UniFi router, I'm running the connection tracking. From the VLAN 10 machine, let me run a curl command against a website that doesn't exist. Because the IP address is in VLAN 20, the traffic will go through the router. So we will see the connection tracking's reaction. Let me run it. From the curl tool perspective, Yes, after a while, it replied an error, failed to connect to the IP address. Then from the client Wireshark, no problem. The first packet from the client, try to send the request to this destination. Because it's not in the same VLAN, the client will send it out without any error. And it is a TCP SYN packet. So it will go through the router. It will create a new state machine. Because router couldn't find a machine with this IP address. So that's why this time the server is not the non-existing VLAN 20 machine. The server is the router itself. It's for VLAN 10. The router couldn't find the destination, and the router will generate a ICMP packet. The type is 3, code is 1. Let me expand the packet detail. You can see the type 3 means destination unreachable, and the code 1 means host unreachable. When this ICMP packet reaches the router, it will use the existing state machine, even though this packet was not sent from the real destination, but it's kind of related to the original SYN packet. That's why the router, the connection tracking, will not create a new state machine. Instead, it will use the existing one and change the state to related. Related means it's not really the directly reply to the original one, but it's kind of relevant. And then the ICMP packet will send out to curl to the client, and the client will respond with this error message. And in the Wireshark session, you see 3 ICMP packets simply because it's TCP protocol, so the client automatically resend the same SYN packet. There were 3 ICMP replies as well. But inside the router, there's only one state machine. As you can see in the connection tracking, once it's timeout, the state machine will be destroyed. Okay, just a short demo to show you an example how we can have a related state. This is another short demo for related states. This time, let's use UDP. Let me run dig command, but this time, let me use a non-existing DNS server. Let me query x.com, run it. After several failed tries, dig command will finish. Okay, it's done. From the client Wireshark, you can see 3 pairs of back and forth. From the client, it sent the regular DNS query to this non-existing server. See who replied? The router. The router replied with a ICMP packet. And there were 3 back and forth, not because of the TCP retransmission. It's because the dig command tried the query 3 times. So it's very similar to previous short demo. It's just this time it's UDP instead of TCP. Okay, creating a related states. In this scenario, because the reply, the ICMP packet came from the VLAN 10 as well. Even if you want, you cannot create a firewall rule to do anything about the related state in this scenario. At the end, let's talk about the invalid state. This type of packet may not be as uncommon as you thought. For example, when you surf the internet, the remote site may not send the TCP packets to close the connection. Then later, it may send you further packet, even though your router already thinks the connection was closed. Those packets will be treated as invalid. So just to quickly demo a invalid packet, let me use hping3. This is a very handy tool to send arbitrary TCP/IP packets. It can be used to test firewall rules. And let me run a command like this. -s and -f means I want to set the flag for both FIN and SYN. This type of settings is not valid, so the packet will be treated as an invalid packet. Let's see now at this moment, I don't have any firewall rule enabled yet. So let me run this command to try to ping from the left side VLAN 10 Linux to the right side VLAN 20 Linux. Okay, from both server and client, there will be pairs of packets. The first one send out a packet with both FIN and SYN set. The remote side respond back saying the packet didn't make sense. But from the connection tracking part inside the router, you don't see anything related to the invalid packet, even though internally it did generate a state machine and the state is invalid. We can confirm that's the case by creating a firewall rule. See, this is the firewall rule I will enable. It will drop the packet from VLAN 10 to 20 if the state is invalid. So let me activate the firewall rule. See, the ping is still going on, right? But see the difference? So from client perspective, it keeps sending out the packets, but because we blocked the packet inside the router, so the server will not reply the packets anymore. It won't respond back telling the client the packets are invalid because the HPing3 tool is still running, so it will keep sending out the invalid packets. But our firewall rules already stopped the invalid packets from harming our system. Okay, it's just a simple random demo, show you some invalid packets which don't really make sense. Okay, this is the end of the video. Thanks for watching.